Thank you, gentlemen. I'll bring your change in a minute.
Here, Bill. It's no good beating about the bush. I'm not all that happy about this contract.
Why, what do you mean?
I've an idea we're biting off a bit more than we can chew, that's all.
Oh, for heaven's sake, Alec, I thought that's just what you wanted. You've been beefing long enough about keeping your capacity fully loaded. Don't tell me now that you can't fit it in.
Oh, we've got the spare capacity, all right. No problem there. But the job isn't just as straightforward as you seem to think. If we're not careful, we're going to have trouble keeping our quality consistent.
But we must, old man. If we don't come up to scratch with this line, we're going to say goodbye to one of our best customers. Now, what's the snag? We've turned out plenty of lines like this before.
Yes, and had trouble, including customer trouble, remember?
Well, at the very worst, you can at least stop the dud stuff going out, surely.
Oh, yes. Nothing easier. Just intensify our final inspection, that's all. And that's not the whole story. There's a matter of deliveries.
Oh, come on. Now, the schedule's not unreasonable.
Not on paper, I agree. We ought to be able to do it standing on our heads.
Well, then?
Well, you know how it is. For days, even weeks, things run well. No troubles, output well up to schedule. Then suddenly you find you're getting too many rejects. By the time you've got things on an even keel again, the output of good products dropped right away. And on top of that, you're landed with a load of reworking or scrap. That's what we're up against.
Well, we've got to find an answer to it.
I know the answer. More inspection. Not just final inspection, but more inspection between processes. 100% inspection. To stop us wasting labor and machine time on stuff that's already defective.
All right, then, let's do that.
Just a minute. That's going to cost money. Who's going to find it? Neumeyer's?
Oh, be reasonable. I can't go back to them now and start shilly-shallying on the price. There must be some other way. More supervision or something.
More supervision or more inspection comes to the same thing. Higher costs.
Well, what can you do? We can't backpedal on the contract now. I'm hanged if we can.
I know it. Well, I suppose I shall just have to do my best as before, juggling a bit with the supervision here and the inspection there and keeping my fingers crossed all the time.
Well, if that's all you can do.
What else is there?
Your change, sir.
Oh, thank you very much.
Excuse me, I wonder if you could light with a light. My lighter seems to be out of action.
Oh, yes, of course.
Here, sir. Take these. Keep them, please. I've got plenty more. In fact, they're my stock in trade. I use them when I run out of words.
That's very good of you. Everett Youngmans. That's a highly respected name.
Oh, you've heard of us then?
Of course, yours is a pretty old established company, isn't it? But do forgive me, I'm afraid I've interrupted your conversation.
It can wait. We were getting nowhere with it anyway.
More's the pity.
Yes, I couldn't help overhearing some of it. I do hope you will forgive my saying this, but I think it might pay you to think about your quality problems on rather different lines.
What's that? Are you in this business too?
Oh, no, nothing like it. But we've had the same sort of troubles that you've been discussing.
Well, that's very interesting. And you've eliminated them?
We've learned how to tackle them, let's say. We've had to. Competition's too keen in our line to allow us to let up on quality.
Who are you with then?
Xeratol Industries. I'm their general manager.
Xeratol? Good Lord, are you Mr. Harper? Well, I'm delighted to meet you. May we introduce ourselves? My name is Shaw. This is Mr. Jennings, our production director. I'm sales, as you probably guessed.
How do you do? Yes, I thought I'd place you both correctly.
I don't want to seem rude, Mr. Harper, but I can't quite see how your experience at Xeratol can have much bearing on our kind of problems.
Well, fundamentally, we both want the same thing, don't we? To keep our quality consistent, in spite of the variability of our processes, materials, and work people. And indeed, to improve our quality performance as much as possible.
Of course. That's what we're trying to do all the time.
Yes, but you're finding too much poor quality, and that's the point. You shouldn't have to trouble yourselves from day to day with things going wrong that shouldn't have gone wrong. You don't want to find poor quality. You want to prevent it.
That's just what I was trying to get at, Alec.
And the answer to that one's short and sharp. Who's going to pay for the necessary extra supervision and inspection?
There are other ways you should consider first. For instance, this job that's worrying you. I presume the specification's okay from the customer angle, but is it satisfactory production-wise? Even if it sets out your quality requirements fully and precisely, and I've known specifications that didn't, is it economical? And is it practical?
Look, we've got a lot of experience.
I know you think it is. But can your processes really cope satisfactorily, economically, and consistently with it? You've admitted they don't always. Do you know exactly what you're up against? Have you got distribution curves for your machines?
Distribution curves? What are they?
They're just a way of showing the variation in whatever you're examining. Suppose, for instance, You wanted to issue all your male factory workers with overalls.
One way of finding their sizes would be to line them up in files according to their height in inches. This would also show you how their height variation was distributed. You'd find relatively few men in the files at each end for the extremely short or extremely tall, but a large proportion in long files near the middle of the range, the men of average or near average height being much more numerous. With a much larger number, such as the male population of a city, the shape of the formation would smooth out to look something like a bell. This bell-shaped outline is the distribution curve, and it's characteristic of almost any measurements where the cause of variation is purely random, whether in human beings or the product of machines. For the product of machines working very precisely, the curve will be tall and narrow, the entire output falling within narrow limits of variation. A less accurate machine gives a broader spread, a shallower curve. So if you want to make something to certain limits of dimension, you can tell from your curve whether it's within the inherent variability of your machine. If the spread's no wider than the required limits, okay. But if the spread is wider, a proportion of your product will certainly fall outside the limits, and you'll want to take some action.
There's nothing new in all this. The question is, what action can I take if my spread's too wide?
Well, can you improve the machine? Perhaps it'll function better with one make of tool than another. Perhaps it needs more frequent tool changing or maintenance. Perhaps it's not being handled too expertly. These are things on which you need information.
And if I find I can't improve the machine, I just go out and buy a better one, I suppose.
That might be the answer. But before that, what about having another look at the specification? Are your tolerance limits absolutely necessary? Could they be widened without prejudice to the ultimate function and quality of the product?
Well, that's not really my pigeon.
No, but if we could keep the design department informed of your real production capabilities, they might be able to think up satisfactory alternatives in cases like this.
You've got the idea.
You still can't tell me what to do if my machines can't meet the specification. The specification can't be altered, and I can't have new machines.
Simple enough. You do the best you can with what you've got.
And that puts us right back where we started.
Not quite. You've got some facts now. You know from your curves what proportion of defective work's inevitable, even when things are running at their best. You can start to balance the real cost of your quality, the cost of all that defective work, and its cost in rectification and extra inspection, against the cost of new machines that can meet your specification, and even reduce your present allowances for inspection and wastage.
Well,
But I'd still advise you not to look on the specification itself as sacrosanct. I'll give you a case in point. This happened on the assembly line at a factory where voltage regulators for cars were adjusted before final inspection. The girls set the cutting in and cutting out voltages by hand using meters, and a pretty close tolerance was required by the specification. Now, this line used to give a lot of trouble because of the high proportion of faulty setting found by the inspectors. Their readings showed too many falling outside the specified limits, so somebody was detailed to look into it. It was soon found that there were variations in the meters used. The assembler's meters didn't line up precisely with the inspectors, and the inspector's meters didn't even match up together. That meant that even the units actually passed as okay were by no means always as specified. And yet customer complaints had been relatively few. So they looked into it a bit further and found that these units would function perfectly well at rather wider limits than those specified. Well, the outcome was that by relaxing the specification somewhat and improving the accuracy of the metering equipment and inspection methods, the acceptable output of the line jumped enormously to the advantage of the product and of the user.
That's a jolly interesting case.
but a rather elementary problem, I'd call it.
Most of our problems are, when they've been solved. Still, the example does point a few morals.
Keep your specifications under review.
Even more than that. Have them make it quite clear not only what quality is required, but how it's to be verified. Another moral is keep in touch with the customer end of things.
I'd like to go back a bit to the distribution curve. Supposing it shows that my processes can do the job, and yet in practice we don't always get the quality we want.
Yes, that sounds more like our particular problem.
Once again, it all boils down to preventing faulty production, not finding and curing it.
That's all very fine, but how's it to be done?
Basically, by inspecting for a quality requirement as soon as possible after producing that requirement, so that you can correct it once if necessary.
Just what I thought you'd say. More inspection. We can't stand the extra cost.
Wait a minute. The nearest place for checking the production quality is on the machine itself. What about making the operator do it?
That's just as bad, even if he did it properly. Look how it'd slow down production.
What's the virtue of speedy production if the product's all wrong? It's another case of balancing the costs involved against the ultimate gains.
I may be thick, Alec, but if our processes can work consistently, why should it be a problem to keep them that way?
Well, perhaps I can clear up that point for you. You remember I told you that a machine working precisely has a tall, narrow curve?
Well, suppose that your tolerances are just as narrow as the range covered by the curve. In such a case, you'll want the middle of your curve, that is to say, the average of your output, to coincide exactly with the middle of your limits. Inaccurate tool setting, wear on the tool, a new batch of material, or unskillful operation may shift that average. When that happens, a proportion of defectives is inevitable. An added difficulty is that it's not uncommon, for economic reasons, to use machines whose total variability is somewhat greater than the specified quality limits, since the percentage of defectives incurred in this way need only be very small. But if you get a shift from the correct average in a case like this, you soon run into big trouble.
I see. And what you're advising is action to stop it shifting.
Of course, you can't stop the machine shifting over a period of time. What you want to be able to do is to detect the shift before it gets big enough to cause trouble, and to remedy it. The man who can usually do this best is obviously the man on the machine. You know, Mr. Jennings, it needn't slow up production.
Of course it would. Stopping work to take measurements, and no doubt filling up forms as well.
It could be done while the machine was running on the next piece.
Oh, I agree it might be possible in some cases. But what about when the operator's continuously employed? Press work, for instance.
Well, some jobs might need separate checkers, but they should work really close to the machine, in time as well as place.
What about machines and processes that produce faster than a man can check?
Why not have the operator take samples while the machine's running? I wouldn't mind betting you in half these cases, the product doesn't get inspected at all until it turns up as defectives in a later process.
No, there's something in that, I admit. But taking samples, oh no, it's not worth the trouble. It could be so misleading. Why, it might even cause a lot of unnecessary hold-ups.
Not a bit likely.
Just tell me why not. Look, suppose an operator takes a sample of, say, 20 parts and measures them. Let's imagine that he finds 5 of them above design dimension and 15 below, but all within the tolerance. Is he going to stop the machine for some fiddling adjustment just because most of them are below dimension? Why, that sort of thing can happen time and time again with samples.
Of course it can, but you can't pin me down with one vague example like that. I'd want more information, and even then, I'm not a statistician.
I should hope not. All those crack brains are good for is filling up forms. I wonder if I can help. I am a statistician.
Oh, no! Come and join the party. It's just warming up.
I thought I might perhaps be able to explain how sampling inspection is made to work reliably.
Oh, well, splendid. You're just the man to help me preach the gospel, Mr. Green.
Oh, Mr. Green, Mr. Jennings, Mr. Shaw, my name's Harper.
How do you do? Well, I didn't want to intrude, but now you'll just blind me with science and smother me with figures, eh? Oh, I don't think there's any need for that, sir. But you see, you can use inspection for 2 different purposes. To verify the quality of the product, singly or in the mass, or to check on the way a process is behaving. Now, Mr. Harper has been talking about checking the process.
Yes, well, the point I was coming to was that if a process is inherently capable of producing the quality, checking and controlling the performance may mean that there's no need to inspect for product quality afterwards.
Ah, quite so. But there is a wider application, isn't there? You can even use the same control methods to get more consistent results from processes which aren't so precise. And that's tremendously useful in reducing the waste that's bound to occur. And you can do it quite safely by sampling, you know, if you do it properly. I'll try to explain what I mean. Take a machine such as an automatic lathe, turning out a long run of items of one particular kind. While the machine's still running, your operator or inspector will take off the last 5 pieces, let's say, and then measure them.
Why the last 5? Wouldn't it give a better idea if you took them at random?
Not for this kind of inspection. The question being asked is there any evidence of change in the machine's performance? You need the last half to answer that.
Yes, of course.
Well, now, if you have a chart with a horizontal line representing the middle of your limits, and you enter in relation to this the measured average of the last 5 off, you've recorded the current performance. If you do the same thing at intervals throughout each day, you see not only the current performance, but also the inherent variability of the machine. Unless that's done on a 100% basis, it won't be accurate. Maybe not, but it's good enough for most practical purposes.
You get the same sort of picture even if you did do it 100%.
And I suppose you'd stop the machine as soon as you see a drift, one way or the other.
Hanged if I would. How do I know there's a real drift? It's no good judging from samples. Completely unreliable.
Ah, that's where your dreaded statistician lends a hand. From his tables, you can draw limits on the chart based on the variability of the process and the size of your sample. These lines show the range of variation you expect when the machine's running properly. So if the results fluctuate between these limits, there's no cause for alarm.
But if a result does fall outside the limit?
Then you must act. It's pretty strong evidence of what we call assignable causes.
And I say it might still be chance, a freak sample.
Well, that's soon checked by taking another sample. It's very long odds against such a freak happening even once.
All right, I see the idea behind it, but it can't be as satisfactory as 100% inspection of the product.
It's a fallacy to think that 100% inspection is 100% reliable. And anyhow, the purpose here is to produce as little scrap as possible, not simply to find out how much you produced.
Look at the protection it gives for your subsequent processes, and reckon that up in terms of reduced scrap and rectification.
Surely 100% inspection is necessary sometimes.
Of course, but not nearly as often as many people would think. Naturally, there are cases where no expense must be spared to protect the quality of the final product. You can run to 200%, or 3, or 400, or even more than that. This aeroplane provides one example. Nothing but the most intense individual inspection would be acceptable for the engines and the structure generally. But even so, the best guarantee of a reliable product is a reliable production process.
You're not trying to tell us you can use a chart like this for small batch production?
Of course not. But wherever you have variability, you want control. And the same principles apply to small batches, even though the techniques differ.
So there's no hard and fast drill that you recommend for improving quality. You just work it out according to the circumstances.
That's exactly it. So long as the methods are statistically sound.
The fundamental thing is that you want to stop any undue production of defectives, using the best means available to that end. On the shop floor, the obvious place to apply the methods is as close on the heels of production as possible, through the operator himself, if it's feasible. Indeed, in some kinds of work, it can even be done by automatic devices on the machine.
That's so. But even then, some kind of over-checking or quality audit is desirable.
Oh, undoubtedly, to check the accuracy of the devices themselves and the condition of the machine.
Well, automatic devices aren't going to help me with my problems.
Thank you. No thanks, Sally.
Now, if somebody would invent a gadget that would keep even raw material quality consistent, that would be something.
Well, now, what's your problem there?
Cost. Cost of checking it. On the one hand, we give intensive inspection to a lot of subcontracted stuff because of the money involved, and yet we don't often have much trouble with it. On the other, we obviously can't inspect every small item that we order in tens of thousands, and yet those are often the very things that run us into quality trouble in production.
Why not look for your answer in a sampling scheme? After all, your subcontracted jobs must have been inspected already by the supplier, who doesn't usually give you much trouble. All you want to do is to confirm that each batch is up to the expected quality. Is that right?
Of course. But sampling's too risky.
No, it isn't. Forgive me for contradicting, but if you're prepared to specify what your acceptable quality level is, the maximum number or percentage defective that you put up with, and the degree of risk you'll take of accepting a batch that falls short of this level, then a scheme can be found that will meet your needs. The way it works out is that you would only have to proceed to 100% inspection when you get poor batches.
You might come to an arrangement with your suppliers, too, about what action you take if your sample shows a poor batch. Will they bear the cost of your doing 100% inspection, or will you return the whole lot and let them sort it out? But of course you'd need prior agreement on quality standards and sampling methods.
That's quite an attractive idea.
It opens up a new line of thought, doesn't it?
But what about the other case, the small items in thousands?
The same sort of scheme can be worked out for them, too, according to the degree of protection you want. In fact, even the Ministry of Supply, for instance, are great believers in such schemes.
But don't forget, Mr. Jennings, you can sometimes spend more in finding defectives than you would save by rejecting them. It's another case where a balance has to be struck.
Yeah, that's understood. But as I see it, it still depends on taking a chance that your sample isn't misleading you.
A calculated chance, statistically calculated, for the risk you're willing to accept. In other words, fixed odds, not a wild gamble.
I see. And I suppose that also applies to sampling when controlling a process.
Oh, certainly.
Well, what about the risk that the sampling inspection won't be done properly? What about when a man's earnings begin to fall through stopping the machine for adjustments?
That's a good point. Your people not only have to understand what you want them to do, they've got to cooperate willingly in doing it, otherwise you won't get very far. Indeed, you might have to consider a different payment system, embracing both quality and quantity.
Pay for good work only. They'd never wear that. After all, faults might be due to something beyond the operator's control.
Well, what about an hourly rate and an allowance for a limited amount of scrap, paying the operator for scrap encountered within this limit, so long as he declares it himself?
Theoretically possible, I suppose, but what an upheaval.
I know, we did it. And our people found in the end their earnings tended to increase because production was more stabilized.
That'd take a lot of thinking about. But I'd like to take up another point with you. You claim that you can apply your control principles to any kind of production.
Yes?
What about when the job's a completely manual one? It isn't a mechanical variability problem there, it's a human one.
Quite so. And because of that, the approach must be rather different. But you can work out a quality rating for the individual and take appropriate actions such as refresher training or a change of task if he or she falls short of it. I know of a case like that in a factory where girls do assembly work on television chassis, including the necessary wiring and soldering. On this line, the work is broken down into a series of operations, and so the responsibility for any faults can be allocated without difficulty. The wiring and the soldered joints are inspected in this case on a 100% basis.
Is that necessary?
In this instance, yes. You only need to have one faulty connection, and you might blow up test gear at a later stage.
Ah, fair enough.
Well, if the inspector does find a fault, he reports it to the charge hand. Back on the line, the charge hand shows the fault to the girl responsible to get her agreement that the fault is hers, and then enters details of the defect on her quality chart. This records her defective production throughout a whole month and indicates the type of fault. The lower part of the chart shows the cumulative results for each month, with a line recording the previous month's performance, and the progress of each girl is kept under constant review. A popular feature of the scheme, which by the way was suggested in the shop itself, is that it requires the charge hand to visit each girl at least twice each day to keep the chart up to date, even when she has no faults. This is appreciated because they like it to be noticed when their work is good, not merely when it's faulty.
Yes, that sounds a good idea. Gives a little stimulus of the right kind.
A splendid idea.
I take it that it can be adapted to cases where inspection on the sampling basis is practicable?
I don't see why not.
You're very quiet, Alec. You'll be giving our friends the impression that you don't take too kindly to new ideas.
On the contrary, I take kindly to any idea that will give me improved quality at reduced cost. But I'm not the man to be rushed into something only to find I've lost on it. I'll say this much, though. I might look a little further into this business of a sampling inspection for raw material quality. Get somebody to put up some plans to fit our case. Might help.
Fine, but why stop at acceptance sampling? Why not consider quality control on a wider basis?
Quality control? Is that what we've been talking about? I always thought quality control was just a maze of statistics.
Statistics come into it to determine the efficiency of the methods you use to control your variability. There's nothing to be afraid of.
All very well. But once you start a quality control department, you'll be overrun with empire-building experts.
You've got the wrong idea. Quality control's more a matter of a new attitude than a new department.
What do you mean by that?
You must start at top management level with a positive policy for creating and maintaining quality. Then you organize for it, along the lines we've just been discussing. Get all departments concerned, from design to after-sales service, to work together for better quality. Then you can fix the responsibility for reaching and keeping to your quality levels squarely on your own production people. You show them ways of doing this, more efficiently and more economically.
That's what I jib at. Changing everything over as you've described is much too big a thing. It'd cause chaos.
But you shouldn't do it all at once. On the contrary, it's most advisable to introduce it gradually, starting with a single department or a single product.
In parallel with your accustomed inspection procedure, if you wish.
Yes, let your people get the feel of the thing in stages. And don't forget, quick information and quick action are the essence of quality control. So from the outset, you must give someone the specific job of liaising with all departments concerned, collecting and feeding back quality information quickly, and indicating where corrective action is wanted. Work along these lines, and you'll find you'll build quality consciousness and quality effort from top to bottom of your organization.
Well, what do you think, Alec? Is there anything in this quality control idea so far as we're concerned?
I don't know, Bill. Could be, perhaps. I'd like to chew on it a bit. In fact, I might even have a few words with the old man about it when we get back.
Good for you. I'll be interested to hear how you get on.
Now, don't start jumping into conclusions, Mr. Harper. I'm a long way from being convinced, you know.
Well, of course you'll want to weigh it up pretty thoroughly, but that's as it should be.
In the meantime, old man, what about our immediate problem, the Neumeier contract? That's what worries me.
Well, it needn't. I think I know a way to modify the specification and simplify production and inspection a bit. I'll get round that one, all right.
Gentlemen, I congratulate you. It's working already. Alec, you're a regular humbug.
What's that? I don't know what you're talking about.